online people can hear, right? They could hear before. So.
Who is online?
Mahmoud and Daniel.
Okay.
Okay, yeah, you're recording.
Okay, well, everybody, thank you for coming. I'm Marco, and this is my PhD presentation, and it's about verification of natural language processing. So first, a bit of background. There is a lot of literature in NLP verification, a lot more in NLP, but there is a small intersection between the two fields, and that's where I'm working. First, a bit of an overview of some NLP concepts. So first of all, vision and NLP share some differences. So first of all, vision is in a continuous space. You can see images. Usually they are between 0 and 1. Continuous numbers, while NLP, for example, sentences, they are in a discrete space. However, verification needs to work with continuous spaces. Instead, for example, of testing that you can test as many discrete samples, a finite number of samples that you want. Verification needs continuity. So in a bit, I will talk about how we can transpose NLP domain from discrete to continuous with embeddings.
There is potentially a controversial statement that verification needs continuous space. Is it?
Yeah, well,
is it
it aims to verify an infinite number of cases.
But continuous, I mean, discrete can also be infinite. The natural numbers
Yeah.
are discrete, but they're infinitely many. But
Yeah,
continuous
that's okay.
is
So, yeah,
explain
uncountably
better
yeah,
what
okay.
you mean.
So in NLP, as we will see in a bit, there are various types of attacks, but usually, for example, word substitutions, you have a finite number of words that you can substitute while keeping the semantic meaning of the sentence, for example. So this would be testing just to test every possible word that you can substitute.
But it's a difference between finite and infinite, not between continuous and
Yes.
discrete.
I think what perhaps makes this statement true that continuous is easier. It's not any verification, it's kind of robustness verification when you want to be robust around certain point in data. And so then it helps to be continuous because you want to draw a shape around your data point and say within that data point, I can guarantee the property. So not verification in general means continuous, but robustness verification kind of.
But you mean that you get to graceful degradation?
Yes, yeah.
Stability.
Stability,
Yeah,
right.
that's what-
Yeah.
Yeah, so it's not as chaotic as on or off, let's say.
Yes, yes,
as
yes,
you would have.
yes, yes. Marco, are you okay that we interrupt you like
Oh
this?
yeah,
Because
of course.
because
You know,
it's-
anytime.
it sounds very strange if I just let it go and say, yeah, verification
course,
needs to be
of course.
continuous only. Okay.
I'm happy you reacted.
Okay, also a different between them is the perceivability to humans, the perceivability of, let's say, attack, of perturbation. So, for example, in vision, if you perturb an image, still by a human will not tell the difference, but the classifier will can be fooled and can change the prediction. But for sentences, it is not as subtle a change. The important thing is to maintain the semantic in the sentence, so that doesn't change. Also, a human can see that the sentence means the same. However, if you put these two sentences next to each other, you will see that there is a difference. They will run and raise it.
Yeah, so maybe this is a good point to feed to the previous slide. Yes, so this it seems like continuous space simply makes the problem statement easier. So we have this panda on the left. Because the space is continuous, I can apply any random perturbation, which is the middle image. And I still know that at the end I have a valid image on the right. So that's where continuous space helps. I can say for any perturbation within this region, I want to guarantee, and still anything within that region will be a valid object. Whereas in natural language processing, it's unclear. If I just make a random perturbation to a sentence, I may get gibberish out of it.
But doesn't it make it easier to verify? In a sense that it's very difficult, I think, to kind of think of all possible attacks you can have, right? Recognizing ORA patterns is very difficult, I imagine. That's exactly why you have them in the first place.
Yeah.
While in the lower part, it actually for the human being would certainly be much more difficult to fool.
Yes,
That's true.
Yeah.
But this is maybe all I want to say is that by
So there's
this
clearly a
argument-
difference between the two
Yeah.
fields. in this
Yeah,
sense.
yeah,
If
yeah,
you talk about, so continuous versus discrete does make sense, but based on this slide, not your earlier.
But what it really shows that continuous space helps you to formulate the problem in a simple way in one line of for all x within the epsilon ball, I guarantee this, and then your
Exactly.
verification.
You have these epsilon balls, you have a metric structure that you can leverage in order to even state stability with a sensible way, right? Here, how do you even state stability, right?
Continuity is not so much helping to verification techniques, say your solver, but it helps you to characterize a property that you want. Yeah.
Then also has a different standing the support of the two types of data. So for example, images, even though they can be different data sets, different kinds of images, different classes, everything, they still lies like in either 0 to 55 integer space or 0, 1 continuous floating space. While for NLP, the vocabulary can be very different, and so also the embeddings will be different, and they're not just equiparable like different data sets and images. So, for example, there are different levels of attacks for NLP. So, character level, you just switch a character, delete a character, add a character, calculate transformations. There also can be word transformation, so you can either add a word or change a word, substitute a word. And then there is sentence level attacks. You change sentence while still keeping kind of same semantic. There is an argument to be made here that sentence level attacks can be like seen as multiple word level attacks. And then multi-level, where you combine one or more of these, two or more of these kind of attacks. Okay, so now,
yes. So from my understanding, so you kind of bring software verification, whatever kind of verification, as a form of defense against attacks. Is that normal in the field of verification, or are there also other approaches to verification? I don't know, right? I mean, not really verified, because you talk specifically about attacks.
Yeah, no, this was just an example. Yeah, and now we're not talking about attacks anymore, to be honest.
But no, you have to answer. Well, it's the simplest. For in AI verification, if you just study the literature, you will see that most often people talk about verification that it's robust against attack. Somehow other properties are not so easy to come by. Well, Matthew is the person who often said either these properties are too trivial that no one states them, or it's impossible to formulate. But somehow in the literature, more often you see robustness against attack verification.
It's what most of the verification techniques were developed to defend against as well. I mean, they can be used, a lot of them can be used for other properties, but they were developed because of people exhibiting attacks and using them.
Thanks.
Yes, so now we're talking about embeddings. First, seems to work with words, we need embeddings, because if we use one-hot encoding, that was in the first iteration of work on NLP, it wouldn't be feasible, because you would need arrays with the length as your vocabulary. So if you have 10,000K different words, you will need 10,000K dimensional vectors. And also they don't hold any semantic meaning. So people developed embeddings that are smaller, always a fixed size, and they also might hold semantic meanings. So for example, the first word embedding, and it's also still the most common, is called word2vec. And then next year, we also deployed Globe. They are both very used. And they're still the state of the art for word embeddings. Here we are talking about word embeddings. So, yes, I can add a few things. The relationship between words, the word embedding here, are obtained using the cosine similarity between two words. That's why they hold, well, semantically, similar words are close together. And you can also use arithmetic operations on these embeddings to derive meaning. So, for example, just as an example, if you take the embedding of, let's say, Berlin, the city, and you subtract the embedding for Germany, and then you add the embedding for France, you will obtain the embedding for Paris. That's so these two, they just differ in how they are trained, word2vec and Glove, but they are very similar in the output and they are interchangeable. They're both state of the art. Questions about this?
It's embeddings of what
Words.
to what? Of words to
Just well, to vectors.
vector spaces.
Yeah, vector spaces. Yeah. Yes, every embedding here is from either words or with assumed sentences to vector space. So, however, in my project, I want to work with sentence embeddings, and I will talk about that in a bit. Why? A few techniques for sentence embeddings have been developed as well. That instead of embedding word by word, they embed an entire sentence and they try to exploit the semantic meaning of the whole sentence. Well, the first to be invented was word2vec, that is an extension of word2vec, the previous word embedding, and it just adds paragraph vectors to the embeddings, and it calculates sentence embeddings with concatenation. Then another sentence embedding is called infercent, and this one uses actually Glove's pre-trained word embeddings to generate the sentence embeddings, and it is trained on natural language inference tasks. Yes. Then the next iteration will be the universal sentence encoder. The novelty here is that it can be used for multitask learning, not only for natural language inference tasks like infercent, but it can be used for question and answer, natural inference, summarization, sentiment analysis, everything. And lastly, the current state of the art for sentence embeddings is called sentence BERT. And this is based on BERT, that is a transformer. A transformer is just a new architecture that came up a few years ago for neural networks. That is the state of the art for natural language processing tasks. So that's the state of the art. And so two sentences here are passed through two BERT networks in a Siamese way, so the weights are fixed. and then to a pooling layer to create a sentence embedding at first, which will be then used as input to calculate the cosine similarity of two sentences. And this is the training process of the sentence bird network. So the sentences, the embedding, sorry, was also a semantics thing for sentences. Sorry, any questions?
Well, if for any two sentences, I know an index of their similarity, I can use that index to embed them into vector spaces somehow. Is that right?
Yes. Yes.
So
Training procedure. I thought we actually don't need two sentences like to embed. You just feed A's, and that's just for training, right?
Yes, that's for training.
When you embed, you just
When
feed
yes, when you embed, you just
So I'm
take
using what softmax
one of
specifier
those.
gives me for every two sentences to calculate the embedding.
No, you actually, and then for the embeddings, you just stop here. You just pass one sentence through
Oh,
verb pooling, and you get the sentence embedding.
Oh, okay, so that's what training. So then you
For training-
provide then is it supervised
Yes,
training?
it's supervised.
So you
yes.
provide what you think that these two sentences are similar. I say yes or no,
Exactly.
and
yes.
then how I train.
Yeah, see, sentence bird
I
is
see.
trained on
Yeah, okay.
20 or 30 different data sets.
We don't do any training of sentence bird
I
itself,
understand.
right?
No, we just took the
Sentence
pre-trained.
bird is trained by some enormous conglomeration of
We
people
wouldn't
on
have the resources.
many parallel GPUs, etc.
Then just a bit of verification. So, for example, there are two kinds of verification techniques, like SMT solvers, like Marabou, and abstract interpretation, like Karen. And that's what we're going to use. In our work, we use Karen. That basically what it does and what we use it for. If we gave a subregion of the space, of the embedding space in our case, that we think, that we create to that because only one class of a data set, then NLP is able to interpret it through the network that we're going to use just a shell classifier because it's not important here. And it will output, it will tell us or try to tell us if the subregion in the embedding space that we chose will only contain one class or not, or like it can either output if it's verified, so it contains one class, and that's what we want. If it doesn't contain a class, or if it cannot have any result.
So do you mean now that the first blue box basically corresponds to the green box at the end, right?
No, the first blue box corresponds to this blue one. It's inside,
right.
and the green one should be.
It's like the
The
equivalent
class-
class
The
of
green one
class.
is the 8, right?
Yes, the green one is here.
right.
So
And the other one is only specific instances of perturbations of that specific 8 that you had.
Yes, this is just an example, two examples I made. So if we have a neural network with fixed weights, so I just chose to be from the right, on the right here, we have one class, on the left the other class. If we pass through this subregion of the space, or this one, it gets verified. If we pass one of these two, it doesn't, because you can see that they contain both classes. Okay, now we're talking about my work, our work actually, that is actually in submission. So this is the project outline. First of all, we're talking about the data set. The data set that we chose is called Are You a Robot? And these are a collection of sentences with the intent, related to the intent, Are you a robot? It actually has three classes, positive, negative, ambiguous. So the positive one contains sentences with the intent are robots, the negative ones, sentences without the intent, and the ambiguous suggest, well, ambiguous sentences. We chose this dataset because we came across legislation, for example, in California state, but even in Europe is being proposed about chatbots that needs to address themselves as chatbots if the user asks. So it is important if user asks, like, are you a robot? Are you human? The chatbot cannot deceive you and must tell you, yes, I am whatever. So that was our motivation for choosing this. Yes, as you can see, the three classes, positive, negative, and ambiguous, is just some data about the data. So here we have some examples of positive sentences that we can find in the data set. Ambiguous ones, you can see depending on the context. It might be a human might think it's yes, I wanted to ask a robot or not. And then negative samples. As you can see, it's not just random sentences. It is trying to leverage the understanding of the network, which also contains words and like robot, person. Like, have you seen the TV show? If it's a person, there was another one. Have you seen the movie? Is this a robot? Right. So there are also some very difficult questions for the models. Then the embeddings, we just use sentence-BERT as it is the state of the art, and we actually use sentence-BERT as many models with different lengths of vectors and trained on different tasks. What we use is the model that outputs embeddings in 3 84-dimensional vectors, and it is trained on all tasks. Then we talk about the geometric subspace that we want to verify, to use in our project. So usually, for example, in computer vision, the classical most common vision space that people verify is epsilon balls. So balls are the inputs, is a radius of epsilon. And because they hold the semantic meaning, they are meaningful because as you saw before in the perturbation slide, just adding a little bit of noise, it's enough to deceive the network, and also humans cannot tell the difference. While if you go further, if you apply too much noise, then it's not anymore a subtle change, and humans can notice it. So that's why it's usually the epsilon ball that's used. However, in NLP, we cannot really use it because we don't know like what's around an input, since it is only discrete inputs translated into continuous space. So we cannot go the opposite way. We cannot go from the embedding space to the sentences. So we decided to try at first to create a convex all around the positive points and pass it through error. Through the verification. Yes, through error. The problem was that it was not feasible to compute. It would take days because of the complexity. And we tried different approximations. At some point, we succeeded to calculate a convex hull, but it was very small that only contained a few samples and it was useless. It was an under approximation. So we then decided to, yeah.
Sorry, just while on the subject of Eps-ball, I think that the key point about Eps-ball, I think these was not that it's not invertible, you can't go back. It's that you have no guarantee that your Eps-ball actually contains any real life perturbed sentences of interest.
Yes, and we cannot.
Right? Because you're
Prove
embedding a
it.
discrete space into a continuous space.
Yeah.
Not every point of the continuous space maps back to a valid sentence. In fact, almost none of the points in the continuous space will map back to a valid sentence. So you draw an epsilon ball around your embedding, but there's no guarantee that you'll actually, and you verify it, but there's no guarantee that any sentences in the original discrete space actually are contained within that epsilon ball. So you're not necessarily verifying anything of interest whatsoever.
So then we decided to.
So
Yeah.
if you could follow up on that a little bit. So how do you get a guarantee if you do a convex hull? There's enough.
Well, there's still no guarantee.
Okay.
But intuitively, if you throw a convex hull around a large subset of the data set, I mean, by definition, you're capturing at least some interior points in the data set that are, so by inference, you should also be capturing, I mean, assuming your data set is relatively representative of your underlying manifold, then
Okay.
you should be capturing.
But we don't really know very much about the density or anything like that of
It's a great question, and the answer is no. It's very hard to.
Yeah.
This is entirely exploratory work. Is this even? Do we even get anything meaningful out of this approach?
But doesn't that mean you should look at the embeddings themselves? In the sense that you can find embeddings that actually might have a guarantee like that, or is that like in abstract interpretation, right? Like Galois connections, but then in the continuous space.
So I think Marco is going to talk about it at the end. I think it's that he's interested in invertible embeddings, possibly in future. One area of direction might be different types of embeddings that you can reason about.
Yeah.
Which regions?
Because I guess you have a lot of liberty in choosing your embeddings in the first place, right? The dimension,
Well, not exactly, because I just use pre-trained models, so there's just a number of them.
Right, because you reuse them, you didn't train them yourself.
Yeah, I cannot train them
But you
myself.
could say, well, if you theoretically know well, it would be nice to have an embedding with these properties, and you could
Yes.
to see if you could train them yourself. Then
Yes.
you can depend on
You
other
probably
people.
need a lot of resources.
Well, it depends. There's a balance between a complicated embedding that captures lots of semantic information, perhaps non-invertible, and it's more simple. It does have nice mathematical properties, but it may not capture as much semantic.
Yes. So we decided to just create another approximation ourselves, called the hypercube. It's very simple and fast to calculate. It's just it's just a cube. For here, it's a square. In the higher dimension, it's just a cube. And around all the positive points. So, of course, as you can see, it also includes negative points inside. So we have realized a couple of techniques to just have positive points inside, because that's what we want. So we want to pass a subspace that only contains positive points, at least from a data set, through error, and try to verify it. So the first thing that we tried was just to, here are the actual data. What's contained inside, these are percentages. So from the hypercube, well, since it's calculated the positive points from the trained data set, it contains all of that. And then it was already good from the start that it contained a lot of positive points and few negatives and ambiguous. So then we decided to shrink the hypercube to exclude the negative points that were inside, while trying to keep it the biggest as possible. Yes, and you can see that when we reach 0 negative points inside, it's very small. also the positive points inside with very few. So the other technique would be to cluster the points and then to calculate multiple hypercubes for the clusters of the positive points.
So maybe, I mean, here all the red ones are connected, for example, right? But could it be possible that there would be like a band of blue ones in the middle,
Yes.
for example? So
Yes.
there would never be, that they would be
absolutely.
really separated.
Yes,
that-
absolutely. So as you can see here, there is a number. That's a number of clusters. That's the number of clusters from where you get 0 negative points inside. With less number of clusters, you still get some negative points inside. So yes. And you can see that it is an improvement from the hypercube and the small hypercube. But then we also decided to apply rotation. That was Daniel's idea. To rotate the inputs in the space to be aligned with the unit space, the axis, right? So that's because the hypercube is calculated in the same direction, the same alignment. So as you can see in this case, the hypercube still contains all of the positive points, but much less than the negatives. And we also apply that with the other two methods. So small hypercube, you can see it contains more positive points. And with clustering, it contains more positive points. And another feature is that you need less clusters to exclude those negative points.
So
yes,
does it mean that you're basically, after applying your embedding, you're applying additional affine transformation? So rotation, you could even scale. I don't know, maybe it doesn't help that much, but
well, rotation helps because
rotation
it
certainly
fits-
helps. But I
yeah.
wonder if it only rotation, or would scaling also help?
no,
Maybe
because it
it's
would
applied.
scale everything, and also the hypercube would scale.
So it's
As
only
well.
rotation that might be useful.
I mean, there might be something else.
But it's like you pre-transform, you're post-transforming something that you've already.
Well, but yes, you're transforming the embeddings, but still the relation between each point remains the same. So you're just moving it, not really transforming points.
But it's a good question. In machine learning, people often embed data in higher dimensional spaces in order to make separable. So you may have data set that's not separable, but embedding into higher dimensions make separable. Marco will tell you a little bit, because we had exactly the question, Daniel particularly, whether the data set that he has is well linearly separable or not
Yes.
to start
That's-
with.
that's
And so
Later on,
corporate
we'll talk about it.
But you're right, you can't view the extra rotation as just another part of the embedding.
Yes,
You could
exactly.
view it as a post.
Right. So it's like you're using somebody else's library, but the outcome of the function that you run is not exactly what you want, but you tweak it or slightly transform it a little bit afterwards. But at least you can reuse their stuff, right?
Yes.
That's,
Yes, and as you can see, rotation helps really a lot. So for example, just rotating the hypercube gets almost no negative points inside. And rotating the small hypercube achieves like a lot of positive points set already, and also the same thing for the cluster hypercubes. And we think that you only need 4 clusters instead of 29 for not having any negative points inside.
So if you don't mind me asking,
Yes.
the rotated small hypercube gives you more test positive than rotated cluster hypercubes. Is this a good thing or a bad thing? Like, does this
So-
mean that you get better classifier by using just one hypercube rather than clustering?
In all our experiments, we go on with using both the small hypercube, the rotated small hypercube, and the rotated cluster. So
Right.
we always use both of them.
What about Philip's question about whether?
Yes.
Like, which one is better, really?
No, for the classifier, they are more or less the same. It doesn't change.
He's asking, is it better to have a higher number
Oh,
or
yeah.
a lower number?
Well, it's better to have a higher number.
Because
Yes, but you have a higher number of positive points in the center,
Yes.
testing set, but you have a lower number in the trace set.
that's
So
what
it's
Incomparable.
But do you care about the train set?
well,
That much.
you care about both. Still, there are positive points, and
no, you care about the test set, right? Because
Right. yeah.
because the train set are the ones that you use to identify the hypercube, and you're interested in what percentage of the positive points in the true underlying manifold distribution of data that these hypercubes are capturing, right? And you're measuring that using the test set.
So
So
this is a bit weird. Is the fact that you're taking something that could be a part of that cluster, and it's better than the cluster itself.
so you're saying it's weird that the number is higher.
Rotated small hypercube, yeah, because it could be a part of the cluster if you chose your cluster differently.
Not necessarily, because the clusters will be smaller, right? Because it's a high dimension, 384 dimension space,
Precisely.
right? So the clusters, you cluster it, and your clusters are going to have smaller radiuses,
Yes.
and a smaller radius results in a 384 exponentially times smaller space in the. So you'd expect the rotated small hypercube to have a larger space, larger.
Yes.
percentage
But
of-
larger is good as long as you don't get test negatives in.
Yes, larger is good. Yeah. So rotated small hypercube is better.
Okay, good.
yeah. But we also try both
Yeah,
of them.
sure. Makes sense.
But it may be better in the sense that it contains a larger proportion of test points, right? And therefore a larger proportion of the true manifold. The problem is that it may be an exponentially larger space, and therefore may be exponentially more difficult to verify, or exponentially more likely that there's still negative examples in that region.
Yeah, that you
but-
just didn't test. And of course, there is more ambiguous ones, right?
Yes. Yeah.
And also testing, you're passing through to verify that there is more hypercube is just one, so if it fails, it fails. While if you pass the clustering ones, you pass at least 4 of them. So maybe one of them can be verified, while the other not. Won't be the case.
I have a small question. Where do you get the rotation from? I mean, is this something that can be learned? Is that also part of the learning process? I mean, how much do you need to rotate it? How
Oh,
is that
it's
figured out?
Yeah, it was Daniel's formula that used the eigenvectors to rotate the embedding space in the unit space.
But this is a deterministic process.
Yes, it is.
Not a probabilistic.
Cheap to perform as well. You calculate the eigenvectors of using the decomposition matrix and then rotate it.
Okay.
Rotation matrix goes in the eigenvectors.
Cool. Makes sense.
And then the classifier, we just use a 3-layer classifier because it achieves already a very high accuracy of 97% on the data set. And an important thing is that it classifies correctly every point inside the hypercubes. So that's important because if it already classifies one point inside the hypercube as negative, then it's not verifiable already. So that's an important feature that it achieves already. 3-layer classifier with value and softmax at the end. It's very shallow net.
And could you then shrink the hypercube? Does that make sense? That you can kind of shrink it to the point that it actually includes only the right points? Does that make sense?
We do shrink the hypercube.
I mean, once you do the classifier and you find that something is not verifiable, you can always shrink the hypercube
Yes.
to make it verifiable. I imagine.
Yes, we'll talk about that later. Sorry. And then the verification part, we pass the network and the hypercubes through Aaron, as I've shown before, but it doesn't verify anything. So, yeah. Yes. So we
Such a build up, 1 hour.
Yeah, what time is it? Okay, I'll go faster. It doesn't verify anything. It didn't work. So we devised additional experiments, and we decided to try and improve training of the classifier to make it more robust, to see if then it is verifiable. So first, we tried to change the training parameters, for example, the embedding models, still sentence bird, but different models with different vector size, and train on different tasks. Tried to change the layers and the epochs, but nothing changed, nothing mattered. So we still had the 3-layer network, and then we decided to continue, and 50 epochs, if anyone is interested. And then we tried to use dot augmentation, that is a technique to improve training by creating or obtaining new samples in different ways, depending on the task or the objective. In our case, we took samples from the inside the hypercube and gave them the label of as positive. And we took samples from the space between a bigger hypercube calculated around all points minus our hypercube and gave them negative label. We tried with 2,000 samples to more or less double the data set, and also tried with 100,000 samples. That would bias the classifier, of course, because it would nullify the effect of the original data set. But a good thing that we discovered is that the accuracy did not drop much, like 1% from on the test set. So that means that the hypercubes are actually representing quite well the distribution of the data. And then after that, we tried the state-of-the-art technique for improving robustness, that is adversarial training. Here we have a bunch of parameters to change, number of samples, number of steps. We use a variant of the PhD algorithm. And then at the beginning, we use a fixed epsilon, as is usually used, for example, in computer vision, because you actually use Eps-ball, so each direction will have the same epsilon. But in our case, with embeddings, each dimension for the hypercubes has a different length. So then we decided to use an adaptive epsilon that adapts to the length of each dimension. Yes, and nothing works.
And is this length of dimension, is that compatible to something like the weight that you assign to that particular dimension?
No, sorry, what? The length of the dimension.
Basically a scaling transform,
Yeah.
right?
Yeah.
Because
Yes.
your hypercubes could be stretched in certain.
Yes.
So
Yes.
this is sort of like a scale.
So unfortunately, so these parameters here, right, are parameters for PGD, right?
Yeah.
Not for. Oh no, yes, sorry.
But-
Yeah, you're right. Yeah.
Yeah, so the adaptive epsilon is just for each dimension in the hypercube, we calculate the length of that dimension, and then we apply a percentage. For example,
I think you have to explain how PGD works in order
Okay.
to get this.
okay. So, well, PGD, that is iterating SGSM plus projection, and SGSM is the sign. So you take the gradient of the network with respect to one input. You calculate the gradient, and then you apply the sign.
Gradient with respect to what?
The input. For each input.
Well, the gradient with respect to whatever you're trying to enforce in a network. So in this case, the gradient when cascaded backwards from what the true length of the thing should be.
Yes. Okay. Yes. Yes. And then you apply the sign, and then it will be multiplied by an epsilon to scale it down. And And then this new vector, this tool vector is added to the original input to modify it to find the worst direction possible. And then PhD is iterating this at the same number of step times, and also apply projection so that it doesn't get out of the space that you want.
So you're trying to find a counterexample, right? In the PGD is trying to find a counterexample to your space. So it's trying to find a point in your space which does not get classified as the right answer. So it's, like it's saying, it starts the point, pick a random starting point, and you look at the gradient and you calculate what the gradient is towards a violation, and then you take some step of size epsilon in that direction, and then you recalculate the gradient, and then to pick a new direction that makes it slightly worse, closer to the counterexample.
So you move a bit every time towards
You
the
move a
worst
little bit
direction.
every time to search the space dynamically.
Right, but now the idea of the adaptive epsilon is that you take bigger steps in certain directions, in certain dimension directions than in others.
Yes.
But it's more to speed up the process than, I guess, than to.
Well, no, because like
Because you have a fixed number of steps, right? Yeah.
Close it, and the door will remain open. Or the door will close, either of them. Close the door, it will come down. It will be different.
But okay, but you have a fixed number of steps. So
Yes.
if you have bigger steps, you can just get further away. There's a bigger chance you get to something that you're interested in.
Yes, but we get already, we set GSM with one step. You get a good counterexample, a good adversarial example, but we use, first find number of steps, and then we plus to 10, and we settle on that. Yes, but in theory, you could move and use as many number of steps as you want. But also there is, we can say that if you move too much, then you can just go around the minimum, like the worst example, or you still can be stuck to a local minimum, so it's not necessary. Yes, and also after all of this, nothing worked. So we decided to add some analysis of the data and embedding space and everything. So we found that the embedded data is almost linearly separable. So Daniel made some analysis with linear classifiers, and we found out that it's 97% linearly separable amongst all classes. And also from the data augmentation experiment that we did with 100,000 sample, that we saw that the accuracy on the test set doesn't change much. We can say that the data in the embedding space is almost separable, and the hypercubes represents the classes, or can represent the classes. Also, the volume of the hypercubes is way bigger, several orders of magnitude bigger than the volume of epsilon ball that we could verify.
Sample was perhaps understated. I think it was minimum 50 orders of magnitude. Possibly hundreds of orders of magnitude.
Yeah, so the maximum that we could verify, just to try for comparison, was 0.0001, and its volume would have been 1 by 10 at the power of 917. While the volume of the hypercube, it was like 6.6 by 10 to the power of 320. So 320 and 1917. So it's yes, a lot of order quantities.
This has significance because everyone verifies epsilon balls, and that's the state of the art. And so we're trying to look explanations why we fail, and we fail because we're trying to jump up several orders of magnitude compared to the state of the art. So no one uses
More than
epsilon
several.
balls of this size to verify anything. Of course, this is not exactly like you simply magnify the epsilon ball, but still.
Yes. And also when we tried, for example, with an epsilon 0.01 epsilon ball, it did not verify. So it was already too big. And that also may be a problem because the minimum distance between 2 points in the data set is 0.085. So, and there are very similar sentences. For example, are you a chatbot and are you a bot? So human perceive them as very similar, also semantically. And they are at minimum 0.085 distant.
And the epsilon balls were how small?
So the one that you could not verify already was 0.01. So
Right.
it could not capture.
Well, okay, so we had some discussion about this, right? It's not that we could prove that it wasn't robust for 0 point.
Yes, we couldn't prove anything.
It's that the classifier spat out, I don't know. I can't
Yeah.
prove or disprove, but
Sure.
Yes.
The one thing we know is that we can verify for epsilon ball 0.0001. So
Yeah.
the only success we ever had was for that. But yeah, there needs to be more analysis,
analysis.
either proof or analysis, but yeah, it does seem to be that the epsilon ball for which we verify is much smaller, much smaller than the distance between 2 points in the data. So this is said in the context that you really can't do epsilon ball sensibly here because there is no indication that if you do such a small epsilon ball, you will actually have any meaningful sentences within epsilon balls.
And then we have some questions about will this volume be actually verifiable in some way, or what's the actual density of the data, because it is not that dense with
Density important because we can't understand where. Well, Iran, unfortunately, the fact that Iran doesn't prove something, it does mean that there are counterexamples.
Yeah.
So it doesn't necessarily mean that there are bad points inside of the hypercube. We just don't know. But yeah, one thing would be to find out maybe other or other not, maybe something happens with the density of the data.
what would be a value of epsilon for the epsilon ball to be meaningful, to find meaningful sentences inside, and can the classifier be trained in a much more precise way to be more robust and to be verifiable. And that's also part of the future work that we might try more to training or embed verification to training, and also develop or study invertibility methods to, or invertibility embeddings to better understand what's in the space as embeddings. Yes. Questions?